Hi, Mr. Dale here again. Welcome to Unit 4, 2D and more D motion. All this really refers to is motion that has both an X and a Y component if we're talking about two dimensions, 2D. More D, we'd have Z, and we can get crazy mathematical higher dimensions, but let's keep it simple. We'll stick with 2D. So basically an X and a Y, and if we're thinking about the usual, X being horizontal, Y being vertical, we can think of an object. Let's say I have a ball, and it kind of follows a path like this. So we could say this is going up and to the right. And furthermore, we could quantify it, being sciencey and all that, and we put axes on it. So we have an X and a Y. So sure, we could say it has an X part and a Y part. But this really is a straight line or linear motion. That really is only one dimension in a case. What if we change our reference frame a little bit? If we're being very official, we'd say changing our reference frame, really our point of view. We're allowed to do that. So really, this only has one component. Hey, if we wanted to call that y, we could just define y as being the direction that the ball is moving. So we really want to say that it has two different motions. What would that look like? Basically, anything that's not a straight line. Curves, zigzaggy, stuff like that. All right, let's go forward. A couple big ideas that I really want you to get here. Let's consider this. We have a river. The motion is, the current is flowing this way. Let me pick up a pen here. I like purple. So let's say the current is flowing this way. Okay, so which boat reaches the other side first? Now the two choices are that we have motion of riverboat with current and without current. So which one's going to get across first? Some people would say, well, it's got to fight the current, so it's going to slow it down. With current, it's going to take a little longer. Other people would be like, I don't know. Gosh, that's kind of weird. Well, let's see. I kind of snuck a peek. That's actually an animated GIF, or GIF if you prefer. And I didn't want us to let you in on the secret, so I kind of cover this up. But let's move off our little shield from here. And I don't want that line. I actually want to just draw this aside. And let's see what we got. Boom. They reached the other side at the exact same time. And yes, this is realistic. But they did not follow the same path. This one actually followed a diagonal kind of line. I'll draw it in for us here. Here, whereas this one just followed a nice straight path right here. The top one with the current seems to have traveled more distance. That's true. That's interesting. So its speed along the line was faster because the current added to that. But notice that they got across the river at the same time. Now I want to talk about a special kind of 2D motion called projectile motion. Officially, a projectile motion is any object that is only under the influence of gravity. This could be something dropped, thrown, shot, whatever. One fallacy that or misconception that people have is that if you throw something or hit something with a racket or shoot it from a gun, is that the object will be speeding up after it leaves your hand, the racket, or the gun. That's not true. Once you let go of an object, be it a racket, your hand, or a gun, it's got all the push it's going to have. Now, if I'm throwing, shooting, or propelling with a racket, I don't know, hitting, I guess, an object horizontally, then that's entirely horizontal. Now, if I hit it upwards, shoot it, or throw it, then it'll have some vertical and some horizontal part. Now, I'm looking in this picture here on the left. Notice that whether I drop an object or throw it sideways, it hits the ground at the same time. And in fact, notice that we have these nice lines. These are exactly the same. These balls are exactly next to each other. And eventually they do hit the ground at the same time. Over here, I have a little more kind of physicsy, I guess, if you want to, where we have a velocity vector indicated. And I'll change colors on us a little bit here. So this is the velocity vector. It has, remember, vector, two components, direction and size. And it's split up into, or resolved is the official word, into two parts. We've got the y, or vertical part, and the horizontal part. Big idea that we've got to have is that right here, the x and y motions are independent. And this is great because it makes our lives so much easier. A couple things to notice in this diagram that I have. At the apex, at the very top, and this is something, notice what's the shape? Hopefully all said parabola. It is exactly a parabola. Anything under a projectile that is only under the force of gravity, unless it's dropped straight down, which is a straight line, follows a parabolic or parabola-shaped course. Notice that there's no vertical component here. It's only going sideways at this point. And then every other place down here, this gets split up into the two parts. You have both a vertical and a horizontal. Notice that the velocity is pointing up and that the velocity is pointing down here, and there's no velocity pointing here. Quick question. What force is actually on it? Let's see. Only gravity. Which way does gravity pull? Down. In fact, that's what down means. So if I'm going to use green for gravity, excuse the this guy here, where is it pulling? I'm going to say that this is gravity down. Gravity's still down here. Gravity's still down here. Does it change? No, it pulls the same. Officially, maybe a little slightly as it's higher, but let's ignore that. It's a very minor effect. Gravity is always down, even though at this point right at the top, it's neither falling nor dropping. Gravity's still pulling on it. Well, what's the force doing then? Oh, right, it's changing its direction from rising to falling. There's an instant where it's doing neither. This is back to inertia, Newton's first law. Okay, let's kind of think about this a little bit more. I really like The Princess Bride. So, quote from there, I do not think that word means what you think it does. It's tenuously related to what we're doing here. You may or may not know, you could probably guess. If you're shooting a rifle at a target that's a reasonable distance away, in general, you don't aim right where you want it to hit, or you'll hit low. In fact, the farther away, you have to compensate by aiming up higher. This statement down here is probably a very commonly held belief. Shooting a high-powered rifle with a high muzzle velocity, that's how fast the bullet travels, is different from shooting a less powerful gun. I think that's true. With a less powerful gun, you have to aim quite a bit above the target, so you have to compensate. But with a more powerful one, you don't have to aim so high because the bullet doesn't drop as fast. Explain why it's incorrect. This is the problem. The bullet doesn't drop as fast. This doesn't matter. If we were to follow how quickly they fall in the same amount of time, they would drop the same distance, just like we did in our previous slide, where each of these slices, each of these balls is right next to whether it's thrown, and we could follow another path. Instead of this one, I could say, well, I'm going to throw it faster, so it's going to kind of fall somewhere over here. Same thing, it's going to fall at the same rate, actually. So this is true, though. I mean, the behavior is the same. That's why people believe it. It works. But it's not quite accurate. The correct explanation is that the more powerful rifle reaches the target faster. So for this guy here, the bullet from more powerful, this is a more powerful, that's a little hard to read, isn't it? More powerful drops less. Why? Less time to target. It travels faster horizontally, so it takes less time. Less time. Takes more time, so it has more time to fall. That's the difference. It doesn't drop as fast. It doesn't drop as much because with a more powerful rifle, it takes less time to reach the target. I hope that makes sense. And in the physics classroom, you'll see some of that. In fact, the boats traveling across there were taken right from the physics classroom website. That's part of your assignments for this module. So solving 2D motion problems, basically because remember they're independent, that means we can work on them one at a time. This is wonderful. This makes life easy. This can involve some trigonometry. So if I have some sort of vector pointing here, we get to put on our geometry, or if you want to be fancy, I guess trigonometry parts, and figure what this is all about. And notice that this vector, we can move this thing. And I think I will. I guess these are grouped together. I'm going to see if I can ungroup these. Yes, I can. Very good. So I'm just going to take this vertical arrow and move it over here. Hey, it's a triangle. We know how to deal with that. And because this is my y part of the, come on, I want a pen. Y part of it, and this is the x part. And I know that these are perpendicular, right triangle. I can use my old SOHCAHTOA or Tom's old ansat and our Coffin Holler, our sine, cosine, and tangent. So if I were to say that this guy, this vector represents 100 meters per second of velocity in this direction. And let's say that this is a 30-degree angle. It looks like it's a little bigger, but let's go with it. I can say that because this is a velocity, I can say that the v sub x is equal to, and let's see, this x part is actually, that is adjacent to this. So let's see which one is adjacent. I use Tom's old answer, sat. So sine of 30 degrees equals opposite, let's see, sat on her over adjacent. So 100 meters per second divided by the adjacent, v of x. I don't know what v of x, I'd like to find out. So a little bit of magic math here. I'm going to multiply by vx, divide by sine 30. Let me know if this is a little confusing. I should go through the steps. And we're basically left with 100 meters per second divided by sine of 30. Sine of 30 happens to be, I'm going to use my calculator actually, you can't see me doing that, so I really don't have everything memorized. But you may remember what sine of 30 is. It's 0.5. I apologize, I made a bit of an error there. Bear with you for just a second. Let this be a lesson to you. Don't do what I do, but let's be careful. So sine is opposite over hypotenuse. So opposite sat on her. This would actually let me find out my y. So from 30 degrees, the opposite side is over here. So this would be opposite side. So that's my vertical component divided by my hypotenuse, which is 100 meters per second. That's the long side. 100 meters per second. And sine of 30 on my calculator is 0.5. You may remember that's a special triangle. Maybe not. Get a calculator, use it. That's fine. So now if I go ahead and multiply this out, I end up with Vy, or the vertical component, is 0.5 times 100 meters per second, or I think we can probably handle that, 50 meters per second vertical. Likewise, to find V of x, we would say that we're going to use the cosine. So cosine of 30 degrees, coffin and Holler for Tom's old hand sign on coffin. Cosine is adjacent over hypotenuse. So I end up with, and cosine of 30, again, you may remember, I can use your calculator, is 0.866 equals adjacent. Now that's V of x over the hypotenuse, 100 meters per second. And through the magic of multiplication, we end up with V of x equals 86.6 meters per second. And I'm not really following significant figures very well. This is how you split the two forces from each other, or resolve the total 100 meters per second at 30 degrees up from horizontal into, it has about 90 meters per second sideways and about 50 meters upwards. So let's try one. Let's do this river question. I think this is kind of an interesting thought. And let's see what's a good watercolor. We'll do a deep blue sea. So this will be my river, river. It's flowing this way. And let's say that the current is flowing at 5 meters per second. Pretty fast river. And let's say that I have a boat that I would like it so that the path it actually takes ends up being a straight path across the water. Now, if I point my boat in this direction, it obviously won't go. It'll end up following something like, oops, sorry, follow something like, the path we saw before. We don't want that. I want it to actually go straight across. So what's going to actually happen, and I'll see if I can actually get my boat to go by itself, is we're going to have to point the boat this way, but it's going to actually kind of sidle across the river like that. So let's see. And furthermore, let's say that the boat engine, it's capable of driving the boat forward at 10 meters per second. So I will say that my total velocity, V boat, I don't really like the yellow, it's very hard to read. I'm going to go with, let's see, more of this color. V of boat equals 10 meters per second. Okay. So I know it's some angle. Obviously I know I'm going to have to point my boat upstream. So let's say that, and this is going to be 10 meters per second. My question is, what angle do I point it at? Let's see. We've got some vectors to deal with. I'm going to go ahead and draw a smaller version of this vector of the current 5 meters per second to the right. And what I really want is to have the horizontal part of the boat velocity of 10 meters per second to be 5 meters per second to the left. That means I would have a net or resultant of 0. And I wouldn't move up or downstream, I would move directly across. That's what we wanted to accomplish, so let's do that. So let's see. Looks like we've got ourselves another triangle. So we're going to have to pull out a little bit of our geometry again. This is a right angle. So let's see. What do I know? I know the hypotenuse. And if I'm going to measure this angle here, theta, this is the adjacent side. So this would be the cosine. So I'm going to go ahead and give myself a little room here. I'm going to erase some of my river here so I have a little room to work. Okay, so I'm going to say that cosine of whatever angle I need is going to be adjacent over hypotenuse. So that would be 5 meters per second over, and what's my hypotenuse? Oh, is the velocity of the boat, 10 meters per second. Okay, that equals, so cosine theta equals 0.5. Notice that the units cancel out, meters per second, so I'm left with just a number. That's good, because cosine of theta should just be a plain number. Now, how do I undo this? I do an inverse sine. And again, I'm going to use my calculator. If you're really smart, you might remember this, but nah, I'm not that smart. So I'm going to go ahead and use my calculator and say that you need to learn how to use your calculator, figure out how to do inverse sines, and you end up realizing that theta equals 60 degrees. So now we know we need to point our boat at 60 degrees, and it will follow the nice path. I think I can, and I'll pretend I can, kind of tricky to do this. I was going to try to move my little boat over, show you the path. It'll go straight across. It's pointing this way, but because of the current, it's going to go straight across. Hopefully that was, you're able to follow that. If not, please let me know and ask questions. All right, well, good luck in the rest of it and try to get all your stuff done on time.